Good morning, everyone. Welcome to the third session. And today we will have first speaker is Dr. Imran, and he will talk about the refraction problem in the context of digital conference.
Okay, good morning, everyone. I hope you are enjoying this Simpa school. Along with the mathematics, you people are having good city tours now. So, uh, okay, just a quick recall what we have discussed. We have been discussing in the previous lecture. Uh, we say that there is a inclusion map between the two rings. We say that A is an algebra retract of B if there exists a map phi from B to A such that phi of I is nothing as the identity of it. And in the previous lecture, you have seen why the retraction problem is so important. So there are a number of problems which are related to the retraction problem, and one of the most important one is the Zariski cancellation problem. Okay, in this particular context, you have seen uh, Costa's problem as well in the previous lecture. And Costa problem says that algebra, uh, if A is an algebra retract of some polynomial ring, so X mean X1 up to Xn of any polynomial ring, then A itself is a K algebra is a K algebra. Okay, these are few things which were discussed in the previous lecture. Just a correction I need to make because in the previous lecture I was discussing two examples where we were discussing about the retraction, and the first example was wrong. Later on, it was figured out that was completely wrong. So I need to make that correction now. So now we are going to extend this particular problem. So retraction problem has been discussed for various algebras, and particularly algebras, the one which are being widely discussed in this particular Simpa school, algebras arising from the combinatorial structures. So today's lecture is somewhat more elaboration on this particular front. This was a fixed one. They started with the wrong board. So in order to say more on the combinatorial structure, I need to define some combinatorial objects. and then we will discuss about various problems, retraction problem in those particular aspects. So firstly, so my first definition is a convex hull a convex hull of d minus 1 are finally independent points in R uh, is given as, for those who are not familiar with this definition, is just, for instance, I have these particular points as V1, V2, Vd minus 1. Maybe it is better to call it D so that I don't have to write much. Then convex hull is given as the collection of all affine combination lambda d Vd with the condition that summation of the coefficient is equal to 1 and for all lambda is greater or equal to 0. Okay, and if you understand, so just you need to pick D finally independent points. Yeah, sorry. In the Euclidean space, R power R. In other words, it is embedded in some Euclidean space. So you just need to pick D affinely independent points, and you make an affine a convex hull of those points, and that particular convex hull is basically called this convex hull S is called D minus 1 simplex. Okay. And just in order, because this is a geometric definition, so there is a geometric realization of it. So affine, for example, so affine hull, it's just those who are not familiar with this particular terminology, it's just like a convex set you are trying to build. But the only thing here, we are imposing a condition that you are taking the points which are affinely independent. And for those who are not familiar with the term of affinely independent, this is the same. You just need to make the vectors of those and just check the linear independent. Take one vector as a center and rest of them, yeah, some mistake. Not necessarily. It can, R can be bigger than D. Yeah. You understand my point now? So it is not necessarily that a simplex should be of the same dimension. Yeah. Yeah, should be equal to 1. And for lambda is greater or equal to 0. Greater or equal to 0. Non-negatives. Okay, for example, a fine hull of just 1 point is just 1 point. And if we talk about 2 points, for those who are viewing this definition for the very first time, so this is better. You should view it from this particular context. You are taking the points which are the canonical basis. 1 point, you always assume it to be the center point. So for any 2 points, you can take this point or this point. For instance, I take these 2 points. They are finally independent. So the convex hull is this one. So for 3 points, Now this is the time you can take 3 points which are linearly independent, affinely independent. So convex hull is nothing but a triangle. And for a convex hull, I can't take four uh, points convex hull in a plane because 4 points cannot be affinely independent. You understand? Because 4 points will give rise to three vectors, and three vectors are not linearly independent in R2. Okay, so there is no possibility here. So for the higher dimension, this is always easier to go in the higher case. So this is the unit 1 point, this is the second point, this is the third point, and the fourth point is this one. So you can think of this as a tetrahedron. And I'm just using this analogy for those who are viewing the definition of convex hull for the very first time. Otherwise, definitely, mostly people are already familiar. So in general, if I collect, so zero dimensional convex, okay, zero dimensional is this one, is just a point. One dimensional is the line. Two dimensional is just a filled triangle. And three dimensional is uh, is this tetrahedron. Yeah. Above definition, R is greater than or equal to T minus 1. R is greater or equal to T minus 1. Yeah, okay. To be very precise, yeah. In fact, I was just mentioning this point according to this. I think you're in this particular context, this is okay. So that's why that there was a D minus. Okay. I started with D minus one, then later on D. I hope everything is clear. Okay. So keeping in mind what he was asking, so if you start with the 4 points and 4 points are affinely independent, so what kind of convex, what will be the dimension of the affine hull is one less than that. That's it. And if you now you have okay, this is the formal definition. So geometrically, the things are easier and nicer to view. So this is the definition of D minus one simplex. And now geometrical definition of simplicial complex. So for the simplicial complex, a geometric simplicial complex usually we denote it with delta, is nothing just a collection of the simplices. We are joining the simplices to form a structure, but joining need to follow a particular rule. That is something I'm going to uh, explain here. A geometric simplicial complex delta is a collection of simplices, is a collection of simplices in RR and it follows but the following rule. Uh, the first rule which it follows is it says that for any PQ which is in delta, P intersection Q should be a face of simplex. Let me also, should be okay in the context, but I'm saying should be a simplex as well. For instance, for example, if you don't understand, so geometrically this is easier to understand. So for instance, I have a simplex, which is a filled triangle. Then the other simplex, which is joined to this one, is this one, and then this one, and this one. Okay, if you see, this is a collection of simplices. So this picture is the collection of simplices, one simplex, two simplex, three, four, and five. So there is always a difference between empty triangle and a filled triangle. Okay. So it is a collection of different simplices. And now the most important thing, what this property says that all the simplices are meeting either in the vertices or uh, if in this particular case, this simplex is sharing intersection with this one is just this vertex. A vertex is what we have already seen. This is a simplex. This is a good example. This is a simplicial complex, but this is not. So here you can see that even I can take the filled triangles. Here we can see that the two simplices are joining with each other, but their intersection is not a full face of either this simplex or of this particular simplex. You understand? That's why I was just trying to write face of a simplex. Okay. Now you understand face of a simplex mean the boundary of a particular simplex. So this is a bad example. This is a simplicial complex. So this is the one property. And the second one is it says that so once you absorb the idea of the simplicial complex geometrically, then we will have an abstract definition too. And the second definition, I think, which follows from above is that if P is in delta, if P is a face or because this is a collection of simplices, and if a P is in delta, then all, so for instance, my P is something like that, then it means that this simplex is made of the triangles. So how many triangles are there? One, two, three, four. So all four triangles are also inside this delta. So we can't have only the tetrahedron inside delta, but not it is made up of. So if a simplex is inside delta, it means all the faces of this particular simplex are also inside the delta. This is the second condition. Okay, these are the two conditions. And geometrically, I hope everything is clear. So very quickly, I will go to the abstract definition. Okay, things are there. So definitely this particular definition and simplices, you have seen the limitation. The things are quite graspable up till here. When we go in dimension 4 or 5 or 6, it is hard to view these convex hull. But for all those who have attended the advanced course of topology, uh, this is a very important tool uh, in order to compute the homologies of topological spaces. Okay, now we have an abstract version of it. And most of the time, this is always easier to have the understanding and then go with the abstract setting. And abstract setting says that let delta be a set of subsets of n of any finite set. So your delta is nothing, just a collection of all collection of subsets of n, such that all singleton are the members of delta. I repeat, all the singletons are the members of delta. And the second condition says that uh, if f is a member of delta, then all the subset of f, then for then G belongs to delta such that for all G contained inside F. So if you have one set which is falling in this particular collection, then all its subsets should be there. For example, it's just like for those undergrad students who are viewing the definition of simplicial complexes for the very first time, abstract definition, you have seen the definition of topology. So you have a collection of sets, then you say that under particular condition, the topology is being satisfied. So this particular thing, and topology is always a subset of a collection of subset of that particular set. So the simplicial complex is also a collection of subsets of that of the ground set, and it satisfies these conditions. For example, empty set one, three, two, three, um, one, two. Okay, I can probably one more vertex. One, two, three, and three, four. So for example, I have written this particular simplicial complex. I'm sorry. Is it visible? Yeah, you can see there. So one thing is quite clear from this particular example, and particularly if you look at this particular condition, this particular condition clearly states that a simplicial complex is totally determined through its facets. Facets mean maximal sets uh, I should call it maximal faces. Under inclusion is called facets. So technique. So there is some dictionary which is associated to the theory of the simplicial complexes. So number one, the members of the simplicial complexes, we call them faces. Okay. So member of this particular set delta, we call them faces. And then those faces, because you can see that the faces are nothing just sets. So there is only one order structure I can define on the set subsets of a given set is the inclusion. And the maximum under maximum members under the inclusion that we call them facets. And this particular example clearly reflect that you don't need to write all the faces. Everything is being determined through the facets. So in this case, I can say that if this is my delta, so we shortly say that delta is basically spanned by, can you tell me which are the facets under inclusion? One, two, three. So, and the other one is three, four. And if you're curious to see what is the geometrical representation of this particular complex, the geometrical representation of 1, 2, 3 is simply a filled triangle, just what I have explained you before. And the geometrical representation of 3, 4 is just you need another vertex and you need to join 3 and 4.
There is a base 4. There is
Sorry.
students at 4.
4 is there. 1, 2, 3, 4. When I wanted to include 3, 4, so you can also, so now you can see that the abstract definition has a geometrical realization. If you are curious to see whether these two definitions are compatible with each other, so they are compatible with each other. Okay, I hope, and there are a few more things. The facets is clear, and the dimension of any member, we can associate a measure to each member of F, and that measure we call the dimension. And the dimension of any face is nothing just the cardinality of that particular set, that the number of elements in that particular set minus 1. So this is a general terminologies which is needed at the moment. So before I move further, because I have to move to algebra now, the algebra associated to the simplicial complexes. Uh, Now, if I talk about this particular ground set, and if I take any subset of this set, that means any member of the power set of this n, then there are two possibilities. Either it is in delta, either it is not in delta. So if it belongs to delta, we call it a face of delta. And if it does not belong to it, we call it a non-face of delta. Okay. And this is something which is really important. So please remember it in this particular case. So this is just the power set of 2n. So any simplicial complex, divide the power set into two parts. In the first part, we have the faces of delta, faces, and there is the non-faces. And in order to define the algebra associated to this particular simplicial complex, this information is really very, very important, very important. And I'm going to explain the algebra related to these problems, related to this simplicial complex. Okay, one of the most celebrated theory in the theory of combinatorial commutative algebra is given by Stanley Reisner. They gave a particular algebraic structure. They call it Stanley-Reisner ring associated to a simplicial complex. So this story is going to relate a polynomial ring with the simplicial complex defined on the set of vertices, in other words, n vertices. So particularly, we are here discussing only the simplicial complex, which is defined over finite number of vertices. Okay, the idea is this. Firstly, in order to have the interaction, so we relate every indeterminate of this particular polynomial ring with each of the vertex here. So by relating this particular thing, we define an ideal. Under this particular relation, we define an ideal, and this ideal is scare-free monomial ideal. And this ideal is defined in this particular way. Okay. One more thing, probably it is, okay, I can go with. So it says that, okay, if I am relating a variable with an index I, so if I talk about a monomial, you have seen the monomial in other lectures. So a monomial, and particularly a scare-free monomial, so regarding to a scare-free monomial, I can relate a vector. And this particular vector is, if the in a general monomial setting, this is just n. And just like I think Thomas introduced nn. So in my natural number, I mean also including 0. So, and how I am relating this particular thing with this this particular setting, it says that, for instance, I have a monomial x1, x2. So related to this particular thing, if I'm It's better to mention here. And if I have, say, 4 variables, so regarding to this particular thing, I have 1, 1, 0, 0. So every monomial, similarly, if I have another monomial U2, which is x1 square, x2, x3 cube. So this particular thing is 2, 1, 3, and 0. So this is a very common way of looking at the monomial, uh, looking through the indices. And the scale-free monomial ideal can be defined in this particular way: xa, a belonging to, this is nothing but okay, is a collection of is generated by all those monomials such that the a, this particular a, and support of a does not belong to delta. Now I need to tell you support. Particularly, I can say support of U1, support of U2. It just comprises on those indices which are non-zero here. Those indices which are non-zero here. And now you understand this particular definition under this particular setting. So a standard Reisner ideal is basically generated by all those monomials, and I will I will discuss what how one can find its minimal generators. So initially, it is just a collection of all those monomials which are whose support is not a member of delta. Yeah. Oh, this particular setting is completely open. I didn't say about this minimal generating set at the moment, and that's why I raised the scare free. This setting is complete. And this is written here. I'm just coming to this particular point. Just coming to. So this is just, and now the task is, how do I know that this ideal is scare-free monomial ideal? Now, if we talk about the support of A, which is not coming on delta, so you can see here, for instance, for this particular simplicial complex, the definition says that you need to draw your attention to the non-faces of the simplicial complex. And non-faces of this particular simplicial complex, if I, according to the definition, if I keep on writing all the non-faces here, this is x1, x4, x2, x4, and then similarly, x2, x3, x4. So this is also a non-face because this triangle is missing from here. Then you can think about other triangles, x1, x3, x4. And similarly, is there any other missing? Okay. And moreover, if you go with the definition, it says that x1 square as well, x2 square as well, x1 square, and all these things. But if you see that, if I keep on writing all the monomials, and we know the Dixon lemma, if there is a monomial ideal which is generated by monomial, it has to be, there has to be a finite set of generators. And this is something which is quite visible from here. X1, X4, X2, S4, if I put in the generating set, then the next one is already taken care of, X2, X4. And the next one is already taken care by X1, X4. So it means now it's time to fill in this particular, this definition is equivalent. That uh, XA, and the same thing A belonging to a set of indices where support of A. Now, instead of saying does not belong to, I say that is minimal non-phase. It's a minimal non-phase of delta. So that's why I made this particular picture. That phases of delta is also important, and non-phases are also important. And which non-phases are really are very important? So in terms of phases, the simplicial complex are defined by the maximal phase, dimensional phases, which we call the facets. And the ideal associated to simplicial complex is basically determined by the minimal non-phases of delta. Okay. Okay, so far so good. And now this ideal has a very famous name. This is widely studied. I'm boring many people in this room who are already familiar with Stanley-Reisner ideal. And the ring this particular ring this ideal is denoted like this. This particular ring is also denoted by K delta. It's called the Stanley-Reisner ring. Stanley-Reisner ring, and people also call it the phase ring as well. Okay, if you look at that particular example, so still I need something more to tell for this particular example. Now it is quite clear. 1, 2, 3, 4. It is quite clear that the Stanley-Reisner ideal is minimal non-phases is x1, x4, and similarly x2, x4. So far, so good. I hope you are with me, those who are looking at the very first time on these particular definitions. Okay, if you look at this particular ideal, so this ideal has a very nice, I, uh, we are the teachers, we always take simple example, and difficult examples are always for the student. Anyways, this example is very, very nice. At least I don't need any computer software to find its primary decomposition. The primary decomposition is quite clear. It is x1, x2 intersection with x4. And this is the time to see the relation of the prime ideal, which is coming out of the primary decomposition of this particular ideal in the context of, again, with picture, phase and non-phase. So if you look at 1, 2, and in the context of the simplicial complex, so what is the complement of 1, 2? Something is wrong with this example. 1, 4, 2, 4. Okay. Okay. The complement of 1, 2 is, yeah, everything is okay. The complement of 1, 2 is the complement of 1, 2 is 3, 4. And complement of 4, and the complement of 4 is these two members are really very special in the context of the simplicial complexes. Can you tell me what are 3, 4, and 1, 2, 3 for this simplicial complex? They are the facets of this simplicial complex. So in any case, so this is not a coincidence that the complement of this prime ideal is giving me the facet of that particular simplicial complex. In fact, this procedure is reversible, and we have a very important result. Oops, sorry. That result says that let I Okay, in the above context, the primary decomposition of this ideal, Stanley-Reisner ideal, is totally determined by the facets of the simplicial complex. It's taken our F is a facet of delta and PF. And what is this PF? This PF is basically generated by the variables and such that the indices, what should I say? Um, okay, so I think XG, so you understand G is where G is a subset of N and F complement is basically G. I hope everything is clear. So far, so good. The Stanley-Reisner ideal definition and this important result. So one can find the Stanley-Reisner ideal in two ways. Up till now, what you have seen, you have a simplicial complex, you have to look for the minimal non-faces, and minimal non-faces will form the generators of the Stanley-Reisner ideal, one way. And then the second way is you just look at the simplicial complex, identify its facets, and each facet will give you a component of the primary decomposition. You just put the primary decomposition, do the intersection, and you get the standardized right. Yes. Yeah, I just write F is a face and I define it in this particular. I settle the PF here. I settle it here. Okay, so far, so good. Okay. Any confusion so far? Okay. Mm, this particular algebra is one of the most important algebra. Those who are just looking for some combinatorial study of the commutative algebra. Yes, Imran. From the yeah, but not always diagram facility is available. Again, for 4 dimension, 5 dimension. I take a very simple example. This is a 2 dimension simplicial complex. So if things got really complicated in general. Okay. Uh, so this part is I'm just mentioning for the motivation. Uh, so one question which arises from this particular discussion is that is this the only case where we are relating some algebra associated to simplicial complexes or combinatorial object? You have seen many of algebraic structure which was discussed in this particular Simpa school, one discussed by Sarah yesterday. And there is an also very important algebra which is called polytopic algebra. I will not go into the detail of the polytopic algebra, but there is a conjecture which is stated for the polytopic algebra, and we will bring that particular problem into the theory of the Stanley-Reisner ideal. So polytopic algebra is basically this is what I'm stating here. It is Gublatze, the work of Gublatze and Bruns. I think I should mention Bruns first. This is the work of Bruns and Gublatze on polytopic algebra. So the structure is something like that uh, for given polytop, definitely in each of my discussion, I will be confining only on the finite. For a given finite polytop P inside Rn, and here I'm talking about the lattice poset, lattice polytop mean the vertices of the polytop are the integers. And the problem is, so they have defined a polytopal algebra. This is called, okay, the persons who are working in the lattice theory, this algebra is coming through the algebra from algebra of straightening laws, where you build a poset and then you take the two elements in the poset, and if they are related with each other, then the relation will give rise to a binomial. So this algebra is quite crazy one. It's with many, many generator. So I think Rizwan worked in Polyomino's ideal. The people are discussing about the toric ideal. So this algebra looks like something which I'm not going to discuss in detail, and something appearing below. And this particular ideal is usually the binomial ideal. And ultimately, this algebra is toric algebra, which is being discussed quite uh, extensively in other lectures. But in this particular work, Gobladze and Bruns have given a conjecture for, the conjecture is this one. So graded every graded algebra retract of polytopic algebra over K is again a polytopic algebra. So from the previous lecture, one thing is quite clear. I didn't say much about the characteristic of K, but this retraction problem really depends on it. And I think when I mentioned for which cases Zariski-Clogier cancellation problem has a solution, so then you have seen that Leena Gupta has given an answer negation to the Zariski cancellation problem for characteristic P. So K, characteristic of K is very, very important. So as I'm not going into the detail of polytopic algebra, but those who are interested to explore it further, I recommend them this particular reference. So there is a series of paper by Bruns and Gubladze. And in fact, they have a series of paper on building the theory of polytopic algebra. And later on, they come up with a book. So the title of the book is Polytops, Rings, and K theory. Okay, so I use this particular part only as the motivation for the without going into much detail of the polytopic algebra. But this conjecture is really important. So this conjecture is this conjecture, because polytopic algebra has the algebra with straightening glass property, what Stanley-Reisner ideal or Stanley-Reisner algebra do have. So there is a natural way to, And yesterday, Thomas Kale was discussing about how to look for the problems. So the other way to construct your own problem is looking at the conjectures and try to translate those particular conjecture in the story you are already in. So now I'm talking about the work of Epstein and Hope. That is their paper in the year 2014. Uh, what they do, they translated this particular conjecture into the language of the Stanley-Reisner ring, in the theory of the Stanley-Reisner ring, and they come up with this particular question. So, what about the graded K algebra retract of Stanley-Reisner ring in the context of above conjecture? So, in fact, they come up with this particular question that whether the graded algebra retract of a Stanley-Reisner ring is again a Stanley-Reisner ring of some simplicial complex or not. And they have found an answer. And on the way, they have introduced many interesting questions as well. So they come up with this particular theorem, an answer to this particular question, that delta be a simplicial complex over n, and k delta be the corresponding Stanley-Reisner ring, then any uh, R which is graded algebra retract of k delta basically this statement is with if and only for any R which is a graded algebra retract of k delta, we have if and only if condition. So you could say that, not any R. R is a graded algebra retract of k delta if and only if R is isomorphic to some k delta W. Uh, this notation is not new for many delta W, but for those who are not familiar with delta W, so for any subset W inside N, we define delta W and we call it induced subcomplex of uh, delta over W is nothing, just it comprises on all faces coming from F, you take their intersection with W. Okay, yesterday I was in the previous talk, I was explaining about how algebra retract problems are being addressed in the literature. So I think, by the way, that conjecture polytopic algebra, which I didn't touch, but the purpose was to just brief you that this theory exists in the polytopic case as well. Those who are interested in studying the toric ideals and toric algebra, it is a widely open area. And Epstein and Hope undertake that particular question. And this is a very natural question to ask. If the conjecture is being raised for polytopic algebra, what about the Stanley-Reisner ring? Whether the algebra, what is the algebra retract behavior of any Stanley-Reisner algebra? So they come up with this particular answer. If R is any algebra retract, graded algebra retract of the Stanley-Reisner ring, so it will be a Stanley-Reisner ring as well of some simplicial complex. But there arises a number of questions. Still, they didn't ask about, okay, what kind of subcomplexes give you an algebra retract? This question is still open. So I'm just mentioning another open question. Again, in the Stanley-Reisner theory, uh, if delta 1 is a subcomplex of delta, the concept of subcomplex, okay. So you know the definition of a simplicial complex. So subcomplex, okay. I think one definition of subcomplex is coming through the induced subcomplex. This definition is completely compatible with what Sarah was discussing the other day. So for any graph, you have an induced subgraph. So for any simplicial complex, you have an induced simplicial complex. And moreover, in order to relate it further, all your graphs are one-dimensional simplicial complexes. Okay. And just like in graph, you know the definition of subgraph. So similarly, that particular definition upgraded into the simplicial complexes theory. And every simplicial complex have the subcomplex structure. One is the induced subcomplex is this one. And the other one, I say that delta is a subcomplex. Oh, this one is a subcomplex of this one. If F is a face of this one, implies that F is also inside delta, because ultimately they are just the collection of subsets. So just you are saying that that collection is contained inside that or the other collection. Okay. If this is a simplicial complex, this is a simplicial complex. I say that this simplicial complex is a subcomplex of this one. This is only possible all its members are already inside this. That's it. And open problem is that to characterize. So if delta 1, uh, so when then whether there exists an algebra retract between their algebras so this is the other problem which is still not addressed in that particular paper, but Hope and Epstein also discuss another problem uh, which is also of interest. Just I'm concluding it. At this, um, it says that if there exists an R, then R will be isomorphic to some induced complex, some subcomplex. The proof says that if R is an algebra retract of K delta, then for this R there exists some W such that the R will be isomorphic to some induced subcomplex. But it didn't say that which subcomplexes give you an algebra retract and which does not.
So this theorem is two-way.
Yeah, this is a two-way. But the two-way, that is one thing I'm saying, that if this happened, then this. And if this happened, that is only the case of the induced complex. So then we have this case.
Isn't this a
But what about not all subcomplexes are the induced sub?
So that means that
So if answer that,
only the case where delta one is induced subcomplex.
then it is already like a blood track of that.
Okay. Then the next thing which is important is the base. Yeah, I think, yeah, this is taken care of. Base of an algebra retract. Base of an algebra retract, it says, yeah,
Here.
I think the point is quite valid. This is taken, this is covered in that conjecture. This group.
Other is not standardized.
For other, this is the if uh, okay, Ali, what is your point?
But delta one is the subcomplex of delta.
Mm-hmm.
So, which apart from the say delta one, right?
Yeah. This is not always, inclusion does not exist always. There are certain cases where this that's not the case. And this exists only when delta one is the induced complex. Otherwise, there are certain issues. And probably that's why I think Shaheen's point is valid. Probably this inclusion doesn't hold for other cases. So probably there are no other cases to look for. That's that. Oh. Maybe I can discuss the second conjecture in my next lecture. But in the next lecture, I will be discussing totally different things. So in the first, only the algebra retract, and the second is, okay, one final point. There are different algebra which is related to a simplicial complex. Standard-Rational theory is just the one. And there is a facet ideal theory. The problem is quite open for that particular case. And similarly, for a simplicial complex, similarly, there are other structures. So one can relate all this particular conjecture, just like Hope and Epstein has translated the polytopic algebra problem into the theory of the K algebra. So one can bring those particular algebra retract problem under the discussion of other algebras. And one interesting point, which was also mentioned, the structure of Cohen-Macaulayness, whether it is preserved or not. And the answer is no. So if your standard if your simplicial complex or standard simplicial complex is Cohen-Macaulay, so the retract need not to be Cohen-Macaulay. And same is the case with Barnes.
Okay, thank you so much. Any question or comment? Yeah.
Sorry, in the very first conjecture on polytopic algebras, is that for any polytope or just lattice polytopes? In the conjecture, I think
that is only for integer polytopes.
Okay.
Only for
Not
integer polytopes. I avoid all the details.
Yeah.
So for the integer polytope, you have to select the vertices in a very particular manner so that it generates the whole lattice.
And simplicial complexes are a case of, they are example of polytope, so that's why it makes sense.
Yeah.
Okay, is there any other comment or question from online audience?
Yeah. Okay.
No questions, so let's thank the speaker again.
Thank you. Thank you.
Okay, now we have a tea break and we will meet again at 11 o'clock.